have light interacting with the specimen and we get changes in absorption, refraction, etc. Same is true for the light microscope. As the light interacts with the specimen, light source here, focus on the specimen, it interacts, light gets bent, racing like that, and we see that image projected through the objective lens, through this body here, this ferret, out through the body here, and out the oculars, onto the retina of our eyes. And that's the image we see. So it's magnified in our case by two sets of lenses, the objectives and the oculars. These are fixed magnification, 10x. We're not going to change those. So the oculars fixed at 10x. But we can change the objectives we use by rotating this turret. So we can have the 4x objective in place, we can have the 10 or the 20 or the 40. So you can change the total magnification by changing the objectives. What you can't change is the focal point of those lenses. The focal point of those lenses are fixed because this lens is always going to be that length from there, right? So the focal point of the lenses is always fixed. So how do you focus specimens? The way you focus specimens is you move the stage up and down. And this is a very difficult concept. So at low power magnification, let's say the 40x objective, we're looking down on the microscope. So when we look down on the microscope, we're looking in this direction. So I'm going to draw that here. We have what's called a depth of focus. So this much might be in focus in the vertical direction. Okay. Now, how many of you photographers, how many use 35mm cameras? It's all digital, right? But in the past, I had GSI say, oh no, you can't define depth of focus as a vertical distance. It's always the horizontal. And I said, just take that camera and switch it like this, and it becomes vertical. And that's what the microscope is doing. You're looking down. So depth of focus is vertical. So for a low power, we have a big depth of focus. For a higher power, the depth of focus is decreasing. For an even higher power, even smaller depth of focus, and even higher, less. So what we see in focus is getting smaller and smaller. Okay? The field of view, which is the circle, the image, where the specimen is also decreasing. So here, the field of view is big, and as we increase the magnification, the field of view gets smaller and smaller. So the cylinder that we see is getting smaller and smaller. Cylinder, because it's a circle with a depth of focus in this direction. So when we look at specimens, we literally optically section them. We see a thin part that's in focus of that specimen, and if we have a higher power, the optical section is even smaller. So as we increase magnification, we increase the ability to have resolution, and those sections are smaller and smaller, okay? So with the microscope, we are doing optical sectioning. The midpoint should stay fairly constant. So as we change the magnification, this should be fairly constant, like that. So when we first look at the specimen, we will use the coarse focus, which is the big knobs at the bottom, the coarse focus knobs, to raise the stage. So what we'll do is we'll have the lowest power objective in place first. Why? Because it gives us the biggest field of view to find the specimen and the biggest depth of focus. Probably the number one thing I help students with is they go in lab and say, I can't find any parameter, I can't find any amoeba. Next week when we look at these things. And within usually no more than 15 seconds, I might find 10 or 20. And I didn't have spontaneous generation, as you know. All I did was I usually almost always switch from the high power to a low power because it gives me a bigger field of view to look for the specimen, plus a bigger column, bigger depth of focus. Now, what happens, and you may not realize this, I never realized this until I started teaching. When we have that slide like this, when we have that cover slip, there's actually a large column of liquid here. So those specimens can be anywhere in that column of liquid. So if I'm trying to use a high power, my depth of focus, that section is so thin, I may not see specimens that aren't there. So by using the lowest power, I can get the entire column of liquid in place. Then looking again from the top down, when I have that slide like this and that cover slip, I have a circle like this. The way I find specimens, I just move that field of view like this, and I just keep doing this, back and forth. It takes you no more than 30 seconds to scan the entire slide. It should never take you more than 30 seconds to find a specimen. Maybe 2 minutes at the beginning, okay? But it's actually very quick. Okay? If you don't have the specimen, just make another slide, okay? No sense wasting your time, okay? Your time's precious, it's valuable. So just move on, okay? Always start with this. Okay? I think that's the number one thing that students don't want to do because you say, after all, I'm working at this power, so why not start there? It works much better, lower power, okay? So anyway, what we're going to do to measure or calibrate that measuring device, the ruler, is that image, since it's in here, will be superimposed upon whatever we see. Now, I wear glasses. My glasses are expensive because I have horrible vision, but if I was wealthy enough, I'd make 100 edges on my glasses. And then when I look at a piece of paper that's very close, I'd see those 100 edges superimposed upon the paper, right? If I hold it further apart, away, are those distances they represent getting bigger or smaller? Larger. If I grab binoculars and look at the mountains, it'd be even larger yet, right? But have the edges ever changed on my glasses? No. So the edges never change on the oculars. The distance between these fibers never change. So what we're going to do is use the ability of the constant spacing of these fibers in this nylon mesh to measure out what distance those edges represent. So your exercise is at different magnifications. You're going to calibrate that measuring device and say, how many of those edges fit in the space of 100 micrometers? The space between the fibers, the nylon mesh, the fibers of the nylon mesh, is 100 micrometers. So if, in this case, can you see the number of ruler marks that fit there? You're going to read that number? It's 40. So if that's the case, 100 micrometers divided by 40 spaces is what? 2.5 micrometers per space. If we change the magnification, the nylon mesh does not change. The edges don't change, but the distance they represent does change. But it's fixed because we only have 4 powers here. So once we calibrate these objectives once, it works every time from then on, right? Because those lenses are fixed in place. Is that clear? Any questions? So that's one exercise. The other exercise to help you understand optical section is we're going to have a slide like this. This is a hollow piece of glass, and this is solid. Now, this can sometimes be confusing. But since we can optically section these specimens, if I had 2 pieces like this, and this one's hollow, and this one's solid, if I'm in the middle of this optical section, I would see an edge here, right next to another edge, and then what would be in the middle if it was hollow? Nothing. Air, right? So I'd see a space, and then I'd see another edge. But if I was in a solid, I would see edge, solid, edge. I would never see 2 lines. So in fact, using optical sectioning, you can tell, so do you think this is hollow or solid? Hollow, because there's the edge, the space between edge. If I was at a different point on that hollow cylinder, those lines would get closer together, or maybe further apart where I'm at, right? If I go towards the top, those lines would appear to go closer and closer together, right? If I go to the midpoint, to the farthest part apart, as I go to the bottom, they get closer and closer together, right? So you can actually recreate the entire three-dimensional image by optically sectioning a specimen at different points in that specimen. Does that make sense? Sounds easy. It's much harder in practice, okay? So you'll do that a lot, okay? So the way the microscope works, there'll be various parts here. It's more important that you understand what these parts do. You'll learn how to use them, okay? When you read through this, you're going to say, I don't really get this. Wait till you get in lab. Wait till the microscope in front of you. Start doing some exercise with them, okay? So here's a light source. We have a field diaphragm here. It has a series of plates, so you can close down how much light there is. So you don't want too much light. There's another set of diaphragms here called the aperture diaphragm. Here's the stage where the slide goes. This thing here flips back and forth. So I'll show you a video shortly. Do not bend this up. Some of the old microscopes that you may have used has a clip where you lift it up and put the slide under. This is not that way. Just take your thumb, just push it, it rotates out, put your slide in, spring closes the back. It will lift up if you use a little force. You can literally bend it out of the plane. It won't work. from then on, but it'll work for that slide, okay? So just use the thumb, okay? We actually had ordered these special for our microscopes, and they were, I think, $40 some a piece for every microscope, because it's a lot better than those clips. Anyway, focus knobs right here. The bigger knob does the stage movement fast. You will want to use that coarse focus with the lowest power objective. Once you have the specimen in focus, you don't need to use the coarse, and you shouldn't use the coarse with any subsequent increased magnification. Only use the fine focus, because it's only going to be out by just a little itsy bitsy, right? So when you thought it was nice clear focus here, maybe it was actually, the center was off slightly. So when you go higher, you can say, oh, I have to slightly reposition. I have to slightly reposition. I have to slightly reposition. So fine focus only with the higher powers. If you use coarse focus, you can potentially damage the slide because there's not much distance between these lenses. So if you use the coarse, you'll basically push the slide into the lens. Worst case scenario, you break the slide. Oh, sorry, that's the worst. That's the best case scenario. You break the slide. Worst case scenario is you break the lens within there. And the lenses are about $300 a piece. So we want to avoid that. When you clean the lenses and they do get dirty, you should only use lens cleaning solution, which we have in every lab room. And it's here. And lens tissue. We have chem wipes out. The chem wipes like sandpaper when you use it on these lenses. So please don't use the chem wipes, only lens tissue and lens cleaning fluid. These microscopes have two major design flaws. We've talked to manufacturers, tried to get them fixed. When you focus this, only use one hand. If you use two hands and you hold the one on the left tight and don't allow it movement and you do the right one, you will snap the rod that goes between those two. So only one, or if you want to do two, very gently hold it so it can spin. That's one bad design flaw. The other design flaw is a 40x objective. That lens is recessed a lot in the holder. So a lot of dirt, dye, things like that get in there. It's really hard to clean. If you have a great image at the 20x objective and you rotate the 40x objective in and you can never get in focus, you need to clean it very thoroughly, okay? Now that having been said, you may still not get it clean. Tell the GSI, I can tell you how my staff do it. Sometimes we actually have to take these lenses out of here and clean them in a different position so we can get better access to them, okay? Bad design flaw, but anyway, that's what it works. So anyway, various parts of this, you'll go through that lab. What you want to do is use two eyes. These are called binocular microscopes. Not easy to do. This is actually, I think, the hardest thing for students to do. What you want to do is close one eye, usually the left, close that eye, get the specimen nice clear focus with your right, close your right eye, and it may not be in focus anymore. So what you can do is you can slightly adjust the focus of this ocular, it's called a diopter adjustment, to compensate for the fact that your left eye and right eye may not be in the same, have the same focal ability, okay? But you gotta close one, then do the other, okay? And it has to be in that order, because the last adjustment you can do is the diopter, okay? All right, does that make sense? Then what you want to do is look with one, you want to create one field of view. If these two lenses are really far apart, you'll see two circles of light. As you push them closer together, you'll see them start to overlap. When they overlap, that's great, okay? And that's what this is trying to show to you here, is that image of pushing the oculars together, first far apart and together, and you see the two field of views overlap into one uniform, okay? So that means you've positioned the interpupillary distance. You can write the number down. Okay? The other thing is I didn't bring my microscope because it's not real effective here, but ideally you'll have your head kind of in a plane like this and not like this, because what happens is you can rotate the entire head this way, and then you gotta hold your head like that. It's not real comfortable, so try to keep it somewhat parallel, okay? Again, you'll practice comfortability, you'll see this, okay? We want to set the best lighting possible. It's called color illumination. That means we have the right amount of light, not too much, not too little, and we position the focal point of that light, of the light source, right on that specimen, ideally. So there's a series of steps you'll do to do that. It's called setting color illumination. You run through those steps. This is just what Dr. Downer talked about in terms of resolution, light microscopes versus electron microscopes, etc. Here's just some interest views here. This is unstained, not a whole lot of contrast, hard to see details. Add stain, you can see more details. We'll do that next week in lab. We'll have you stain your cheek cells with a dye that's specific for DNA. Here's an illustration of a translation electron microscope image here. You can see surface topology really well. This is what you'll see when you close down the field of view. So there's a aperture diaphragm, there's a field diaphragm. Field diaphragm is the one closest to the base of the microscope, closest to the light source here. That's the field diaphragm. When you close it down, you'll see a circle of light like this. Now you see nice sharp edges. That's because the position of the condenser has been done properly. The way you set the position of the condenser is using this condenser adjustment knob here. Now I made a video that I will try to show you. Hopefully it's going to work. Anyway, we want to get nice sharp lines. That means you position it, and then you open it till it just fills the field of view. Now this is a rectangular image, so I can't illustrate it properly. If I had a circular image there, you could see it, but when you look, it's circular. This just shows you the calibration with more resolution, better ability to see that. You can figure out which one's on top, which one's on the bottom. So let's just take, and this is the isolation seawater plate, streak, nice isolated colony, pick one of those. PCR, we'll talk a lot more about this. I mean a lot, okay? We'll do this PCR reaction, we'll end up with lots of that DNA. We'll run it out in a gel, we'll quantitate it, we'll send it, the gel will separate the bands, we'll quantitate it and send it out for sequencing. Now, I'm going to show you this movie. Okay, and I cannot, unfortunately, post it on BSpace right now, because we only get 1 gigabyte, and this one image is 800 and some megabytes. So let's just quick watch this. Let's see if I can get sound to work. Okay, so right now, don't know why I don't, you don't see a thing, do you? Well, okay. So what I'm going to do is try to get this to work for next time, okay? I'll try to post it on BSpace. What it is it's a image of the microscope. As you change the knobs on the microscope, what's happening to the image. So when you change the field diaphragm, what happens? When you change the aperture diaphragm, what's happening, okay? So I'm going to try to get this to work.
Professor, I'm Ben Schroeder. I got your email. So 9:15, does that work for my GSI as well?